Hello, I'm Guruprasad Upadhya. In this lecture, we'll discuss more problems, some special problems of the calculus of variations, and how to solve geodesic curves or how to get the geodesic curves using calculus of variation. Here is one question. Find the curve passing through the points x1, y1 and x2, y2, which when rotated about x-axis gives a minimum surface area. That means one curve is there. If you rotate through about x-axis, that curve makes one solid. So it's a surface area. Find that curve, that surface area becomes minimum. Such a way, make the curve, it joins the point x1, y1 and x2, y2. Surface area is nothing but integral x1 to x2 2 pi y into ds. See the logic here, 2 pi y. See, when you rotated about x-axis, y is that length, it becomes one circle. Circumference of the circle is 2 pi r, that means 2 pi y, and that circle from x1 to x2, it becomes surface. Therefore, the surface is nothing but integral x1 to x2 2 pi y ds, or ds is nothing but root 1 plus y dash square dx. We know that ds by dx is root 1 plus y dash square. Therefore, ds is replaced by root 1 plus y dash square into dx. Now, this is your surface area. The question here is, find the curve such that this surface area is minimum. To make this minimum, here f is nothing but, ignore this constant, f is y into root 1 plus y dash square, and apply the Euler's equation for that f and solve it. So you will get the required curve. Now this f is y into root 1 plus y dash square is independent of x. There is no x here. Therefore, Euler equation becomes f minus y dash into dou f by dou y dash is constant. If it is independent of x, remember this is the formula of Euler equations. If f is independent of x, dou f by dou y dash, how to differentiate f partially with respect to y dash? Y is constant, square root of 1 plus y dash square is 1 by 2 root y dash square into derivative of y dash square is 2 y dash. Therefore, dou f by dou y dash is y into y dash by here square root of 1 plus y dash square with respect to f. So that is y dash by root 1 plus y dash square, 2 cancels, and into y dash is there. So it is y dash square by root 1 plus y dash square, and f is nothing but y into root 1 plus y dash square minus y dash into dou f by dou y dash equal to c. Once again I repeat, here y is constant, root 1 plus y dash square derivative is 1 by 2 root 1 plus y dash square into derivative of y dash square is 2y dash. Cancel 2, y dash by root 1 plus y dash square into y is there. So y into y dash by root 1 plus y dash square, that is dou f by dou y dash multiplied by y dash. So it is y dash square by root 1 plus y dash square. So with minus sign. Now, so very simple, you can simplify this, multiply first throughout by root 1 plus y dash square. Here it becomes y into 1 plus y dash square minus y dash square. Multiply throughout by root 1 plus y dash square. So y plus y dash square minus y dash square. Y dash square cancels, y remains, y equal to c into root 1 plus y dash square. Y equal to c, y dash square cancels, y equal to c into root 1 plus y dash square. or root 1 plus y dash square is y by c, square both sides. 1 plus y dash square is y square by c square. Take one right side. Y dash square is root 1 plus here y dash square. Take one right side, y square by c square minus 1 or y square minus c square by c square, that is y dash square. Take square root, y dash becomes root y square minus c square by c. So this is your y dash. Y dash is nothing but dy by dx. Now separate the variables and integrate. Now dy by root y square minus c square equal to dx by c. Integrate. Remember the formula here, it is cos hyperbolic inverse y by c. How we got the integration of dy by root y square minus c square, that is cos hyperbolic inverse y by c, because if I substitute y is c sin hyperbolic theta, see here y is c sin hyperbolic theta, y square becomes c square sin hyperbolic square theta minus c square. Take c square outside, it becomes c root sin hyperbolic square theta minus 1. And we have one formula. In trigonometric formula, cos square theta plus sin square theta is 1. In hyperbolic function, cos hyperbolic square theta minus sin hyperbolic square theta is 1. Therefore, cos hyperbolic square theta is 1 plus sin hyperbolic square theta, or sin hyperbolic square theta is cos hyperbolic square theta minus 1. Now, if I substitute y is cos hyperbolic, so not sin, cos hyperbolic theta, y is c cos hyperbolic theta, then cos hyperbolic square theta minus 1 is sin hyperbolic square theta, its square root is sin hyperbolic theta, and dy is, if y is c cos hyperbolic theta, dy is c sin hyperbolic theta d theta, cancel c, so it becomes 1. Integral of 1 is theta. Theta is nothing but y equal to c cos hyperbolic theta. So y by c is cos hyperbolic theta. So theta is cos hyperbolic inverse y by c. That is how we got the integration. It's very simple. Just see the formula. Just compare with the trigonometric formula. Integral of dy by root y square minus c square is cos hyperbolic inverse y by c. Now integral of 1 is here x by c plus k, that is integrating constant. If I take the common denominator here, I am going to write c into k is some a, x plus a by c, that is cos hyperbolic x plus a by c is nothing but y by c. Therefore y equal to c into cos hyperbolic x plus a by c, and this is nothing but catenary. Catenary is nothing but a hanging chain problem also, that is catenary. So the shape of the curve is, it is like a heavy chain is hanging on the in the two fixed endpoints. Okay, so that is called catenary function or curve. The hanging chain problem is also same type. A heavy chain hangs freely under gravity between the two fixed points. Show that the shape of the chain is catenary. The concept is same, but the question is here, let A is x1 y1 and B x2 y2 be the two fixed points of the hanging chain. Now this chain is hanged like this. When this chain is stationary, that means no any movement in this chain, then its potential energy is stationary. Let rho be the density of the chain. You know what is meant by density? The potential energy of the chain is rho into g, gravitational force, into y, this length from the ground, that is y, into this length of the arc, that is ds, from x1 to x2. This is potential energy of the chain. And if I substitute ds is root 1 plus y dash square into dx. So y root 1 plus y dash square into dx, rho into g. So this is constant term. Now this potential energy is stationary. You are going to find the functional f is function, that is y into root 1 plus y dash square. It is similar to the previous question, that is surface area. Here f is y into root 1 plus y dash square independent of x. F minus y dash into dou x by dou y dash is c constant. If it is independent of x, this is your Euler equations, and we already solved the same type. So simplified, final, you get the same answer. Cos hyperbolic inverse y by c, that is x equal to x by c plus k, everything is same. Y equal to c cos hyperbolic x plus a by c, and this shape is called catenary shape of the curve y, that is catenary. So one example of that catenary shape is heavy cable, electric cable hanging. That shape, it is like a light parabola shape. It hangs like a parabola shape. So that is called catenary shape. Okay. Next one is what is meant by geodesic? A geodesic on a surface is a curve along which the distance between any two points on the surface is minimum. Here, along the surface, take one curve, and distance between any two points is minimum. Then that the curve is called, the curve must be in the same surface. And if the distance is minimum, then that curve is called geodesic. That is definition of the geodesic on a surface. One example that we already discussed the same problem. Show that the geodesic on a plane or straight line. It is nothing but take any 2 points on the straight line and you are going to find the curve such that distance between the 2 points is minimum. So it is nothing but shortest distance between any 2 points on the plane. Therefore, the shortest distance, so we got the shortest distance along the straight line. So that curve is called geodesic. So that we already discussed in the previous lecture. So let y equal to y of x be the curve joining the point A and B in xy plane. So this S is the curve, and y equal to y of x for which S is minimum, that is called geodesic. Geodesic means that curve must be minimum. Here curve is nothing but this arc length is minimum, shortest distance. And we know that S is nothing but integral x1 to x2 ds. ds is nothing but root 1 plus y dash square dx, and this is your f. F is independent of x and y, and hence Euler equation becomes y double dash is 0, and integrating y dash is m, again integrate y equal to mx plus c. So this is straight line. This is required geodesic on the plane. Okay. One more example. Find the geodesic on the surface. Given that arc length S is given here, this is arc length. Find the geodesic on that surface. Geodesic is nothing but this arc length, of that arc is must be minimum, that we know. So S is minimum, then you get the geodesic. The shortest distance between any 2 points is along that curve is, that is minimum. And hence if the arc length is given, just minimize it. That means just substitute f on the Euler equation, so you'll get, and simplify and solve that equation, so you'll get the geodesic. Here A geodesic on a surface is the curve along which the distance between any two points on the surface is minimum. Therefore, this S is minimum means the f root x into 1 plus y dash square. This satisfies Euler's equation, and clearly it is independent of y. No y is here. When you substitute in the first Euler equation, dou f by dou y dash becomes c constant, because dou f by dou y is 0. First part is 0. D by dx of dou f by dou y dash is 0. Therefore, dou f by dou y dash is constant. Now f is here. Just differentiate partially with respect to y dash and equate into c, constant c. Now here root x is constant, just keep outside root x. Now root 1 plus y dash square derivative is 1 by 2 root 1 plus y dash square into 2 y dash. So cancel 2. So y dash into root x by root 1 plus y dash square equal to c, constant. This is dou f by dou y dash. Now just square this and rearrange. Y dash square by 1 plus y dash square is c square by x. C square by x. Take the reciprocal. 1 plus y dash square by y dash square is x by c square. 1 plus y dash square by y dash square is nothing but 1 by y dash square plus 1. Take on the right side. So 1 by y dash square is x by c square minus 1, or x minus c square by c square. X minus c square by c square. Again you take the reciprocal. Y dash square becomes c square by x minus c square. First simplify this and take the reciprocal. Then you take the square root. Y dash becomes c by root x minus c square. Y dash is nothing but dy by dx. Separate the variables and integrate. You will get the solution. So dy equal to c by root x minus c square into dx. Integral of dy is y, and we know that derivative of root x is 1 by 2 root x. 1 by root x integration is 2 root x. Therefore, it is 2 root x minus c square. Here c is there, so 2c root x minus c square plus some integrating constant k. So this is your required geodesic. If the arc length is S is this. Okay, if the arc length is given, just solve it, you will get the geodesic. This is about 5th module. Okay. If there is any complicated questions, so you can directly ask me, call me, or just send one message to my email address. Thank you for listening.